How are you doing?
I'm fine.
Busy.
This is a micro.
Good to see you. How you coping?
I'm fine.
Thank God. Let let's see if I think some few others will join and then we'll start. Okay, Alan is joining. Hi, Alan. Alan, can you hear me? Alan and Esther.
Yes,
Can you hear me? Alan,
says
how are you doing? Okay, so let me add an S2. Hi, Ernesto.
Hi,
How are you doing?
I'm fine. Thank you.
Good to hear from you.
Yes.
Esther,
Thank you.
Esther, I've not heard your voice. Esther, can you hear me? Alan, is Esther close? Okay, so I think it's 4 minutes past 10. So we'll begin our session. You're all welcome to our first online session. The coronavirus is keeping us away, but that should not stop us from learning and progressing. So I'll start today's session. We'll start with a quick recap of what we already know. Then we'll zoom into higher or deeper content. How many of us have watched the videos?
I have.
Okay, Isaac. Ernesto, have you?
No, I haven't.
Okay, not a problem. Joel, have you got the videos? Joel? Joel, have you watched the videos? I think we can unmute our microphones. I believe there's not going to be so much noise. If the noise gets too much, we'll put it off. But you can turn on your microphones, so we don't have to be going back and forth, back and forth. Joel. Joel, can you hear me? I don't know if you cannot hear me. That's why I want you to turn on your microphone. So
I can hear.
okay.
yeah, I can hear.
Okay. Good, Joel. Thanks. So in today's session, we'll have a quick recap. We all know what robots are. We've seen them before. We are all not very new to the concept of robotics. So as we explained and as we saw in the video, the concept is to create machines that are like us. Now, in creating machines that are like us, we needed to give them some very key features that makes them capable of doing the things we do. For every robot you would have to deal with, either in the industry, in the home, wherever you meet a robot, you are sure to identify these three parts of the robot. These are the senses of the robot. In this case, we call them the senses of our robot. And we have all seen a couple of sensors before. We all know these sensors. What sensor is this?
Ultrasonic.
An ultrasonic sensor. We'll be looking at a deep concept of how it works. What sensor is this? We know that.
Touch sensor.
Come again.
Touch sensor.
A touch sensor. Good. So we need the sensors. The work of the sensors, as we all know, is to help the robot know what is happening in its environment. The key part that I want you to grab is that, you know, engineering has to do with you, the person engineering the system. There is no limitation or there is no restriction as to what you can do. So don't lock it in your mind that you want to see somebody's design online before you will be able to create your own robot. You should be able to imagine the concept of what machine you want to build. Once you imagine that concept, you identify what we call the functional requirement. It looks like a big word, but it's nothing big. When we say functional requirement, who can try to explain to us what he understands or she understands by functional requirement? I've never mentioned it before, but on top of your head, what comes in mind? When we say the functional requirement of a machine or a robot or a system, functional requirement, who will try? Alan is speaking. Okay, Alan, your hand is up.
It means that what you want your robot to do.
Exactly. Thank you. Any other? What you want?
What action you want?
Anybody wants to add something? Okay, so I'll roll with what Alan said. What you want your robot to do? What are the functionalities? So assuming you wanted to build a robot that will be a firefighter, then you know that this robot should be able to, let's say, spray water or sprinkle water, or should be able to detect when there is fire. Once you have listed all of those things, my robot should be able to detect fire. My robot should be able to sprinkle water. Let's say these are the two functionalities that you identified as the functional requirement of your robot. Then the next thing that comes in mind is, what senses will a robot need to be able to carry out these functionalities? Are you following? So if you have a robot, or if you want to build a robot that can detect fire, then you ask yourself, what sensor will I need to be able to detect if there is fire outbreak somewhere? Anybody on top of your head, what type of sensor do you think will fit for such a robot? Anyone to try? You wanted to build a firefighting robot or a firefighter robot. What sensor? Looking at the functionalities, so we've listed two functional requirements: able to sprinkle water, able to detect fire. Now, what sensors will you need on such a robot? It doesn't have to be one of the sensors you know. You can just assume what sensor will be required and what the sensor should be able to do. Okay, Ernesto.
A heat sensor.
A heat sensor, thank you. You see, because wherever there is fire, there is heat. So no one will have to tell you, okay, let me join. I think Jaden is joining. So no one is going to tell you that, hi, Shan, how are you?
It's all fine.
Okay, thank you. Okay, so welcome to the class. We are already rolling. So, Ernesto, as you said, no one will tell you that you need a heat sensor, but from the functional requirement we listed, the engineering mind you have told you that a heat sensor will be required for the robot you are about building. What other sensor do you think you would need? Anybody? Alan?
The temperature sensor.
Temperature sensor, so heat sensor, temperature sensor, good. So all of this, you see, now you are thinking about sensors that have to do with heat, fire. There is one sensor I'm expecting that I've not heard. Anybody wants to think wild? You are looking at detecting, okay, Ernesto? Ernesto, I'm
A
listening.
sensor to detect how much water is left.
Come again.
A sensor to detect how much water is left.
A sensor to detect how much water is left. So let's say water level, are you following? A moisture sensor, water level sensor, that is good. Okay, how about a smoke sensor? Because there is no fire without smoke. So you might not see the fire, or the robot might not be able to detect the fire, but it should know that once there is smoke, there is likely going to be fire coming out from there. So now, after you have thought about all of this, you have identified all your sensors, the sensors you need to build this robot. That is phase one. Then you would also come and think about the second part of the robot. Human beings, after our senses detect, we need to respond to what? To what our senses are seeing or feeling. Are you following? So once we have the senses, we also need to identify things that we can use to respond to what the senses are feeding into our system. That is why human beings have hands. We have a mouth to speak. We have legs to walk. Are you following? So these are our action part, the part that we use to respond to what? Our senses input. So you then have to say, okay, these are the senses I require or I need because of the functional requirement I have listed. Now, so we have talked about the senses. Now, the next thing we are looking at is the action part. What parts do I need to give my robot to perform actions if it has to be able to quench fire? So what actuators? The action part of a robot are called actuators, coming from the word action. So we said robots have senses. They also have actuators for performing actions. So in building your robot, now you've identified your senses. Can you identify what action part you need for such a robot? What actuators you will need for such a robot? So Sean, we are looking at a robot that quenches fire, and we are identifying the sensors we will need and then the action part we will need for that robot. Ernesto and Adam are giving us heat sensor, temperature sensor, water level sensor, I've added smoke sensor. These are the sensors. Now we want to see if the robot is able to detect smoke, detect heat, detect temperature change. It has to respond. What part will we have to equip our robot with to be able to respond?
We would have to equip it with like a motor in the form of a pump so that when it detects the fire, it can like send water to the fire.
Okay, thank you, Sean. So motor in the form of a pump so that when it detects, it can send water to the fire or pour water on the fire. Isaac, your hand was up.
It will obviously need wheels to move so that I can get to the place where the fire is to spray the fire.
Exactly. So it will need wheels to be able to move because the fire is not stagnant. The fire can be at any place. So it needs to be able to move. So you see, now depending on the functionality of the robot, you are beginning to identify the action parts you need for your robot. Now, the third one, or the third skill you will now need, is your creativity. And that has to do with you. It is in you. How do I connect these parts together to make it easy for the robot to perform these actions or these functions that I need it to do? So the shape of a robot is limitless. You just have to be creative. You can pick inspiration from existing robots. You can look at Curiosity, the one that NASA sent to Mars, and say, oh, this is how Curiosity was built. I want to build a robot in that model, but mine should have a water pump. It should have a smoke detector. It should have a temperature sensor. So you can then construct your robot. But we added one part to say that for the robot to be able to coordinate the sensors and the action parts, you see, you don't start sprinkling the fire when nothing has happened. You only sprinkle the, you don't start sprinkling the water when there is no fire, which means the sensors and the pump or the sprinkler must be coordinated. Their actions must be coordinated. The sprinkler should only be working when the sensor is saying there is fire. Are we there? So look at the choir. There is a choir master who is standing and conducting, telling when the alto should sing, when the bass guy should sing, when the treble should sing. It's just like that. Someone has to coordinate the various parts. Are we there? So after getting these things, we need something to coordinate the actions of the sensors and then the actuators. And what do you think that will be? In a robot, now you have your sensors, you have your action parts. What would you need to coordinate the behavior of these two parts? Ernesto's hand is up. Sean, I'll come to you.
I think you need a processor.
A processor, thank you. So a processor, a computer. Sean, let me hear from you also.
An intelligent brick, or like a microcontroller.
Good. So intelligent brick, microcontroller, processor. When you hear all of these things, they stand for one thing: a processing unit. Are you following? So a processor, a microcontroller, an intelligent brick, a computer, all of these are called or come together to form what we call a processing unit. Are you following? So we need a processing unit, which is like the human brain. So our brain coordinates our senses and then our action parts. That is the work of our brain. So virtually we are giving our robot a brain. And that is how we constructed a simple robot in the first video I sent. So in the first video, what we sought to explain is this basic concept. Now, we have a challenge on 28th August, and I need 2 members. The challenge is simple. It is part of the RoboFest online competition. There is no rule, there is no competition. On that morning, RoboFest will announce the challenge, just like I announced this morning. We need to build a robot that will fight, or a firefighting robot. On the fly, on that morning, in 2 hours, we are required to come up with what sensors we will need, what actuators we will need, what intelligent brick we will need, and how we will interconnect them and program them to perform the action. This competition is coming up. I'm admitting someone. I say is joining. So this competition is coming up on the 28th of August, and I'm going to nominate 2 people from here to join that competition. It is creativity. It is creativity. You have to be creative enough to think about the problem they will announce and come up with. Hi, I say.
Is it on? Have you switched it on?
I say, how are you doing?
I'm fine.
Okay, so guess it, we are already in class. So on the 28th, we want to test ourselves on this concept that we have just learned. Your creativity is the limit. Once you know the problem at hand, You list your functional requirement. After listing your functional requirement, you will come up with the sensors you need, come up with the actuators you need, and then with your creativity, you build a robot that suits the functionality that you identified. Then the next phase will be the programming. Are we all clear? Any questions so far? Anyone has a question? Isaac.
So why are you going to get a water spraying sensor to build a firefighting machine?
Thank you. So for every robot that you want to build, these sensors exist. These sensors are built on the principle of, I'm coming, I'll show you something. Okay. So beyond the sensors that you have seen in the EV3 robots, there are a lot more sensors. Who has seen this sensor before? Okay, Sean has seen one before. Isaac, have you seen this before?
No.
So
I've not seen it
gas
before.
or smoke sensor.
Sit down. You sit down and concentrate.
Look at this. Anybody seen this sensor before?
No.
Okay, Ernesto, you mentioned the heat sensor.
Yes.
Yes, so there is a heat sensor.
Okay.
So all the sensors you can imagine, once you imagine them, they are available for purchase. Once you imagine them, they are available for purchase. And even those ones that are not available for purchase, you can request for sensors to be made. There are different kinds of sensors that you can have to work with. So Isaac, you don't have to worry much about what sensors you will need. Once you come up with your requirements, the sensors that you need can be provided. We can purchase them. Now you are working with the EV3, so you only work with some limited sensors. But as our concepts go high, we'll start bringing in Arduino boards, Raspberry Pi, and the rest, and then we'll look at sensors beyond just the EV3 set of sensors. Isaac, are you okay?
Yes.
Okay. Any other question? So we can move on. Ernesto?
No, no questions.
Okay. So let's move on. So after we have built this robot, it is time to program the robots or to give them instructions. It is with these instructions that they will coordinate their paths. So once they have instructions, the instructions will tell them what they should use their sensors for and what they should use their action path for. But in trying to do this, in the second video, I tried to introduce you to some few engineering concepts. They are not big. They sound big in the video, but in this class, we'll make it very simple so that when you watch the videos, you realize that it is very basic. So in engineering, we have what we call, a system. When we say a system refers to anything, any device, or any environment that we want to have control over. Do you understand that? What a system is? A system is any device or environment or thing that we want to have control over. In engineering, so when you hear the system, so look at the system units. That is your system. A system can be your room, the room in which you are sitting, having your video conference. That can be your system. So the moment you want to have control over your room, then you want to have control over that system, which is your room. Do we get it? Has anybody heard the word smart homes before? Smart homes. Hello, I say.
Yes.
Have you heard smart homes before?
Kind of.
Yes.
So, what did you hear about smart homes? What's a smart home?
A smart home is a home that can operate itself, clean itself.
Come again.
A smart home is it's like a computer that no human being or anything will have to clean. It can clean itself.
Okay, it can clean itself. Okay. Sean, your hand is up.
A smart home is a home with devices that can operate automatically and detect when a problem is needed to be solved. Like, let's say there's dirt under a sofa and then there's a machine over there using sensors. It can detect what that that's there, so it will go there to clean it. And then let's say maybe the gate is coming, there's something on the car that will help the gate detect when the car is near it.
Okay, good. So, Ernesto, do you have something to say? Joel.
No.
Joel, a smart home. I want to hear your voice. Oh, okay, so Joel's mic doesn't work, so okay. Alan? Alan?
Yes.
A smart home. What is a smart home?
Yes, sir. A smart home stored automatically.
That's what automatically?
Like it's controlled automatically.
It's controlled automatically, or it gives you control. It gives you the chance to control the things in the room. So when we take a smart home, for example, then it means the system. What is the system here? With what I said about systems, what would be the system in a smart home?
Your TV.
So the TV could be a system. I follow. So a TV is one of the systems in a smart home. Are we there? Any other person?
Yes.
So we said a system is anything, any device or environment we want to have control. So now with what you understand about smart homes, let us identify some systems in a smart home environment. Esther. Come again. Carol. Carol, have you joined? I say, any other, apart from the TV, which Alan is saying is one of the systems in a smart home, any other system you can identify in a smart home?
The lights.
The lights. Once you want to have control over the lights, once you want to have control over the lighting in your room, it means that light becomes a system. Are you following? So anything in the home that you want to be able to control becomes what? A system. So the light becomes a system. Your TV becomes a system. Your refrigerator can become a system. Are you following? So we are saying that a system, and we can even say the house itself is a system. So I introduced in the second video I sent, I introduced you to a concept called control systems. We all understand the word control. So control systems is an engineering approach to controlling systems. We have looked at what systems are. And we are saying that there is a concept called control systems. And once you study control systems, you have the ability. Okay, so Kofi Wari has joined us. The session has started and we are ongoing. So I'll Kofi Wari, follow. Thank you. I thought it was Karen, but I now realize it's Kofi Wari. You just said the message. Thank you. So when we say control systems, with the idea of our current understanding of what systems are, we have seen. Okay. So just for the sake of those who are judged, let me just do a quick recap. So the introduction, we have looked at, or we are looking at the basics of robotics. We have gone through how to build a simple robot, which was what we shared in our first video. You know, we sent 3 videos within the week. The first video was how to build a simple robot. Now we want to control robots. But to be able to control robots, we are not just limiting our scope to robots. We are going to talk about a simple engineering concept. And to understand that concept, we were talking about what we call a system. Sorry, I got disconnected. So we were talking about what a system is. And we said a system is anything or any device or any environment that we want to have control over. So we talked about the simple concept of what we are calling a smart, which is a very popular upcoming technology, smart homes, smart. Then we said if a home is smart, it means, Sean was telling us that if a home is smart, then it means the home should be able to control some of its activities. Like if there is debt, the home should know there is debt and maybe send a device to go and do the cleaning. Then we said, okay, so if we have a smart home, with our idea that a system is anything we want to have control over or be able to control, what are some of the systems we can identify in a smart home? So Alan mentions a TV set. Asiya mentions the lighting system. I can mention a couple of them, like the air conditioning in the home, like let's say the gates, the doors in the homes. These or all of these devices become systems that we want to control. Now, currently, how do we control things? You have a TV, you have a remote. You use the remote to control your TV. You have a light, you have a switch. So you use the switch to control the light. But these are not smart enough. So we want to go on and talk about what engineering calls control systems. The principles behind systems that are under control. Once we understand this, in every engineering environment, in every setting, we can work our way around building intelligent systems. So the principle of control systems is nothing strange. It might look big in the video, but it is as simple as there are systems and you want to control them. So when we talk about control systems, which you will see in the second video as classical control systems, this is what we are talking about. There are systems, we want to control the systems. Now, let's move into control systems, the concept of control systems. To control a system, there is something we need to know about the system. So let's say you all play games, right? Do you play games?
Yes.
Okay. Yes. February. Do you play any game? I want to use that to explain something. Okay, I'm not here.
Yeah, Mike, we play.
To use that concept. So if you play games, what type of game? Just name one game you play. One of them. Which game do you play? Any of the kids?
Football.
Come again.
Football.
Football. Okay. Do you play football video game?
Yes.
Good. So when you are playing a video game, the football or soccer as a video game, the players in there are the systems. And you want to control those players. Are you following? You want to control those players. But there is something you should know about the players. You need to know what we call the state of the players. And I'm going to explain state. The state of a system are the possible situations the system can be in. It's still high level. I'm going to talk about it again. I'm going to define that again. The state of any system are the possible conditions it can be in. I'm going to use a human being as an example. A human being can be in the sleeping state, can be in the walking state, can be in the dancing state, can be in the running state. What other state do you think a human being can be in? Anybody? Sean?
The falling state, when they are falling down.
Falling state. Any other?
The walking state.
Walking state. So you see the states. Isaac, your hand is up. Let me hear you.
Dying state.
Come again.
It is state.
The dying state.
The dying state. Are you following? So the state of a system, take it that they are the things that the system can do. So a human being can walk. When he starts walking, we say he is in the walking state. Are you following? A human being can dance. When he starts dancing, we say he is in the dancing state. Usually, a system cannot be in more than one state at a time. Some of the systems can be in 2 or 3 states at a time. Are you following? So, in the second video I sent, you would see me talking about a concept called finite-state machines. Finite-state machines. Anybody understands the word finite? Sean, your hand is up. What is finite? When we say something is finite?
A finite is like a yes or no command. So let's say there's a chocolate factory and you want it to be 45 degrees. The chocolate is in the factory meant to be 45 degrees. And there's a machine at 9. If there is below 45 degrees, it's a yes or no. So it will come up. The minute it goes above 45 degrees, it will come down.
Okay. Okay. Thank you, Sean. The English word finite. Ernesto, I need your help. When you use the word finite in English, what does it mean? Finite. When we say something is finite in English, what does it mean?
It has an end.
It has an
Like,
end.
it's limited.
It's limited. Good. I like the word it's limited. Can anybody Google the meaning of finite and read it out? I'm doing it here too. You've done sets, a finite set. Have you forgotten? Finite set. What's a finite set? You did sets in mathematics. What is a finite set?
A finite.
According to Wikipedia, the onion, also known as the bulb onion or common onion, is a vegetable that is the most widely cultivated species of the genus Allium.
Finite sets. Anybody to help us? What a finite set is?
A finite set is like a set that has the limited number of numbers or
elements, right?
members, yes.
Good.
Yeah.
Look at that. That is what we are bringing into engineering. It has a limited number of members. So if I take the set, let me write something. So if I take a set like this, 2, 4, 7, and I end it, I have a finite set with 3 elements, right? Right?
Yes.
So when we say something is finite, it means it has a fixed number of elements. It has a fixed number of elements. It can have 3 elements. We can have another finite set that has 4 elements. Or we can have another finite set that has only 2 elements. We can have a finite set that has 10 elements. We can have a finite set that has 200 elements. Do we understand? So if a finite set has 20 elements, it means it cannot go outside 20. It is only 20 fixed elements. Are you following? So if we say a machine has finite states, let's understand. We have spoken about state already. That states are the possible things we can do. A human being has working state because human beings can walk. So when a human being starts walking, he's in the working state. Are you following? So the things we can do are our states. So if we talk about a machine or a robot, the states of a robot are the things the robot can do. So I have a robot that can sprinkle water. The robot can sprinkle water. The robot can move. The robot can turn. These are 3 states that I have defined for this robot. Are you following? Are you following? I say, pick your robot.
Yeah.
Show us your robot. The one you have there. The first robot, the golf ball. Good. So that is a robot. What are some of the possible states of that robot?
The motors.
It can kick. Are you following? You remember the golf ball? It can kick. So we can say that that robot can go into the kicking state. It can move. It means the robot can go into what? The moving state. Are you following? Are you following? So if the robot can perform 5 actions, then it means that robot has 5 states. Are you following? So if we say a finite state robot, it means it is a robot that can perform a specific set of actions. Do we understand? Do we understand? So when we say a finite state robot, it means this is a robot that is limited to a certain number of actions. Now, from this, we can say that we can have a 2-state finite or a finite state robot with 2 states. We can also have a finite state robot with what? 3 states. Or a finite state robot with what? 4 states. Are you following? Are you following? So we have under finite state machines, you can have, or under finite state robot, you can have a 1-state robot, a 2-state robot, a 3-state robot, a 4-state robot, a 5-state robot, a 6-state robot, or even a 100-state robot, depending on the number of actions that the robot can perform. Do we understand? Do we understand that? So if I say this robot, if I say this robot here is a 3-state robot, what does it mean? Sean?
It means that it can perform 3 actions.
Good. It means the robot can perform 3 actions. The actions can be, let's say, grabbing, moving, and maybe spinning. Are you following? These are the 3 states of this robot. It is a 3-state robot. Are you following? Someone can build a robot to be a 5-state robot, which means the robot has 5 functions. So remember, we started from you listing your functional requirements. Each of your functional requirements will end up as one state. Are you following? Each of the functional requirements you will write down will end up as one state. So if you wrote 10 functional requirements, then it means you are likely going to end up with what? A 10-state robot. If you wrote down 3 functional requirements, you are going to finally end up with what? A 3-state robot. So in the second video I shared, we spoke about finite state machines, and that is what we meant by finite state machines, what we have explained now. It is finite state robots in our case because we are dealing with robots. Are you following? Now, as I said, human beings, we have a lot of states, but it is not all the time that we are exhibiting all our states. When there is no song, I don't exhibit my dancing state. Are you following? And when I am sleeping, I don't exhibit my eating state. So at any point in time, I will have to trigger one of my states to take action or to take control over me. Are you following? Are we there? So with that in mind, we then say that for a finite state machine, after we have defined a state, we should be able to write a program or a software that will tell the robot what state it should exhibit at what time. Now, before I exhibit any of my state as a human being, or what will cause me to exhibit, let's say, my dancing state? What will cause me to exhibit my dancing state? Joel, type something. Joel, type something. What will cause me to exhibit my dancing state as a human being? I have a dancing state, but I don't exhibit it all the time. What do you think might cause me to exhibit my dancing state? Good. Joel says when a song is played. Are you following? Now, when the song is played, how will I know that a song is being played? How will I know?
You hear it.
I will hear it. What did I use to hear?
Your ears.
My ears. So you see the sensor? So it means that a machine is built with a number of states. It's built with finite states, let's say 10 states. But it will wait for the sensors to tell it which of its states it should trigger. Are you following? So you can build a machine to have watering states, moving states, but whether it will start watering, a sensor must say there is fire, so start what? Watering. Are you following? So to build a finite state machine, you define all the states, but you will connect a sensor to the states and say that this state should only trigger when this sensor says it is time to what? To trigger. So just like human being, I have a dancing state, but my dancing state will only start when my ears tell me that there is a song what? Playing. Are you following? Are you following? So in the second video I shared, that is what we talked about. We talked about finite state machines. What you saw there was just a 2-state machine, which either had the state of heating chocolate or cooling chocolate. The video 2, we spoke about a finite state machine which only had 2 states. And the 2 states were either heating a bowl of chocolate or cooling a bowl of chocolate. But whether the robot or the system will be in the heating state or cooling state was dependent on a temperature sensor. That is what we discussed in the video 2 I sent. And then in the video 3, we went on to program finite state machine. So now that we have discussed what a finite state machine or what a finite state robot is, I will need you to join me as we go on to demonstrate how to program a finite state robot. We can look at a 2-state, a 3-state, a 4-state, a 5-state, even a 100-state robot. So before we move on, any question? Any question on finite state machine? Done.
If the robot is moving and doing all those actions, if the sensor is also looking for things, is it like how come it's not considered as an action, but like it's looking for like things?
Ask the question again.
Like, let's say a robot is supposed to follow a line. If the sensor is looking for the black line, but then the robot is moving, that's an action. How come when it's also like the sensors are trying to detect the black line, it's not considered like a state? Yeah, or a state.
Good question. So you can design the sensors looking for the action or the black line as an action. You can design that. So look at this. I'm coming. I'm going to build something simple for you to look at. So if I have this, can we all see? Can we see? Can you see what I have in my hand? Can you see what is it? What do I have?
It's like a sensor, but it's on a motor.
So I have an ultrasonic sensor attached to what? A motor. Are you following? Which means as this motor turns, what is happening? The sensor is also turning. So let's say this ultrasonic sensor is looking for intruders. Are you following? The sensors act of looking for an intruder in the environment. Are you following? It's also now an action. Are you following? So as long as you are controlling the action, so in this case, as you add, the sensors behavior of looking for what is happening in the environment is the sensor is not attached to anything, then it is not an action because you are not doing it. Are you following? Are you following? The action in this case is the moving of the motors, which is what is causing the robot to move. But the action in this case is the moving of the sensor. Are you following? So Sean, that can be an action, provided you have control over it. Like I've built here. Good question. It was a good one. Any other? Okay. So we have looked at control systems. Classical control systems. We've seen what a system is. We've seen what control is. Then we have moved on to a specific type of control system called finite state machines. Under finite state machines, we have looked at what we mean by a state or the states of a system, which are the possible actions the system can perform. We have looked at the meaning of the word finite, which means it is locked within a specific set of actions or specific set of elements. So when we say finite state, it means the machine is limited to a finite set of actions it can perform. So we said we can have a two-state machine, which means that machine is limited to only two possible actions. A three-state machine, which means the machine is limited to three different actions. A four-state machine or a four-state robot, which means the robot is limited to four different actions, which means a 10-state robot will be limited to 10 different sets of actions. Are we there? So today we've looked at one, how to build robots. We looked at the sensors, how to connect them. We are all not new, so we rushed through that. How to connect them, the intelligent break. Then we moved on to control systems. We've talked about finite state machines. Let's look at how to implement a simple finite state machine. So the first one was simple. If we want to design a two-state machine for this robot, which meant this robot can either go forward or go back. It means going forward is one action and going what? Back is another action. Are you following? Are we there? So that is what we have in the second video. But don't limit it to just going forward and going back. So if we say going forward is one action and going back is another action, then it means this becomes a two-state machine. Now we said before this robot will decide whether it should go forward or go back, there should be a sensor telling the robot that it is time to go forward or it is time to what? To go back. So in the second video, we look at the old thing we all know how to do by using this sensor, a touch sensor, connected to the robot to say that when the robot detects a touch, it should move to the going forward state. And when the robot does not detect a touch, it should move to what? The going backward state. My idea, or the idea for this video, this first 3 sessions, is to make you understand the concept of classical control systems. So, okay, I'll share the links to the videos. I'll share the links to the videos. Kofuara is asking, I'll share them. So now, to program this simple robot, I'm going to share my screen. Can you see my screen? Can you see my screen? Any response? Can you see my screen? Sean? Sean? Sean, can you see my screen? Ernesto? So I will share my screen. Sean, can you see my screen?
Yeah.
Okay. So now we are moving on to programming this robot. So if you look at this robot, what port is our sensor connected to? Sean?
Our sensor is connected to port 3 on
Port
the
3, right?
EV3
So
block.
what we are saying is that this robot has 2 states. Whether it should be in the moving forward state or moving backward state depends on this touch sensor, which is connected to what? To port 3. So to program that robot, what we are going to do is simple. We will move on to our programming environment, which we have here. We are all familiar with this environment. So I start a new program by going to File, then New Project, then I select Program. So that opens up a new project for me with one simple program in there. We are saying that for finite state machines, before they decide on what state they will be in, their sensor will have to tell them what to do. So we will say that we have a sensor. So at this part, we have the action blocks, flow control, then sensor, right? So we move to what? Sensor. And then we have a touch sensor. So I pick the touch sensor and say that there is a touch sensor. It is connected to port labeled 3. Are you following? We will use that touch sensor to what? To measure the state. Are you following? So we are measuring the state of the sensor, whether the sensor is in the pressed state or what? Not pressed state. Are you following? Once we measure the state of the sensor, we can use that state to tell the robot which of its 2 states it should get into, whether the moving forward state or the moving backward state. But to be able to do that, we will bring in this block called the switch block. Now, okay, we will bring in this block called the switch block. I'm going to explain what the switch block does. The switch block is used to create a number of states. Remember, we talked about what? Finite state machines. And we said a finite state machine can have 1 state, 2 state, 3 state, 4 state, 5 state, as many states as possible. Are you following? Are we there? So if I had a finite state machine that had 3 states, then what I will do, watch this carefully, what I will do is that I will say that this switch block, the switch is like the switches on our wall. What do we use them for? To turn on or what? Off the light. Are you following? Are we there? Those switches have the ability to control only 2 states. Are you following? In one state, the light comes on. In another state, the light goes what? Off. Now, have we used a ceiling fan before? Have we controlled the ceiling fan before?
Yes.
Have you seen the switch of the ceiling fan?
Yes, it's like a no.
How many states has it got? Can it control? How many states can it control?
5.
5 states.
5.
Are you following? So you can see there is a switch that can control 2 states. There's another switch that can control what? 5 states. Now, your gamepad, how many states has it got?
About 12 or 13.
So it can, your gamepad can control about 12 or what? 13 states. It is a switch. Your gamepad is a switch. Each press on your gamepad puts the system in one particular state. Are you following? Sometimes a combination is needed to create even more states. Are you following? Are we following? So look at the switch block as the switch on your wall for your light, the switch for your ceiling fan, your gamepad, your TV remote. How many states can it control?
A lot.
A lot. Are you following? Because the TV has a lot of states. So depending on the states, 1 minute. Depending on the state, the possible state of your system, you realize that the switch that you are giving to control the system can have so many controls. Are you following? So that is the block you have here, the switch block. So assuming we were creating this switch block to control a system, a ceiling fan, and it means we need how many states? Sean.
If we're controlling it if we're setting it to control a ceiling fan, we will need 5 states.
5 states. So to do that, look at what I'm going to do.
Fan.
Listen, to do that, we'll say that this switch, are you following? I will click on this part of the switch, the mode of the switch, and select numeric. Are you following? Are you following? So I select numeric, and I see what? 1 and what? 0. Are you following? I can change this one to, let's say, 2. Are you following? Now I need 3 more states. So what do I do? I see there's a plus sign here. Can you all see the plus sign? Can we see the plus sign?
Yes.
So I can click on that, and what does it do? It has added 1 more state. I can name that what? State 3. Are you following? So if I were designing for a 3-state machine, then I will have what? I can put 1 action here, 1 action there, and put what? Another action for what? For 3, which means, oh, we lost Kofi Warren. Are we getting it? So now we have a 3-state machine or a 3-state switch that can be in state 1, and we can put an action here. In state 2, we can put an action here. In state 3, we can put what? An action here. Are you following? We could also say that, so it's a ceiling fan. We will add what? Another state, and say that is what? State what?
State 4.
4. Are you following? We can add 1 more action and say this is what? State what?
State 5.
5. But remember, your ceiling fan has the off state. You have 1, 2, 3, 4, 5, and you have off. Are you following? So it means I can add what? 1 more action and say, in the next state, let me name that state state 0. Are you following? So that we put off the fan in that state. Are we there? So you see how we are creating finite state machines. You will have a sensor that is used to control what? The states. And then you create the number of states that you have. So if it was a ceiling fan, let's say that this is, I'm coming, let's build. Minute. Just 1 minute. I'll do the figures. So if I were building a ceiling fan or a fan, are you following? What I have here is what? A motor, right? Right? Connected to what? The blades of the fan. Are you following? And if I turn this motor, the blades will do what? Will turn. Are we there? Are we there? So I can say that in state 1, if I connect this motor, if I take this intelligent brake and connect this motor to what? To port labeled, let's say, let me use the same intelligent brake. So I have this. And then we have our touch sensor connected to port label 3. So touch sensor is on port 3. Sorry, a minute. I need something harder. Just 1 minute. Let me build a simple system for us. So if I connect this, if we connect this to port C, the port labeled C of this robot, are you following? And then we connect a touch sensor to the port labeled 3 as we had done. And we say if we'll start with a two-state machine and say for a two-state machine, we've looked at how to create a 5-state switch. So I'm going to start with a switch and say that this switch has 2 states. For a 2-state machine, we can use logic, which is either correct or what? Wrong. That is 2 states, either yes or what? No. Are you following? So if the touch sensor is pressed, the state will be yes. And if the touch sensor is not pressed, the state will be what? No. Are you following? So here we don't need multiple states, we only have 2. I have this motor connected to port C. So I would say if the touch sensor is pressed, then I will pick the action, which is the large motor connected to port labeled what? C. Are you following? And say it should be turned on at a speed of, let's say, 30. Are we there? If the touch sensor is not pressed, then I would say that the large motor, so in this first state, the motor is on. In the next state, I would say the motor is what? Off. Are you following? So there is a 2-state machine or a 2-state robot that can either turn on a fan or turn off a fan, but it cannot regulate the speed of the fan. Are we there? Are we there? So if I pick this program and I put it in a loop to say that this instruction which we have created, we select the whole instruction and then we drag it into our loop to say that the robot should forever obey this instruction. If I download this instruction by connecting and we can see it detects, it will detect our robot. Good. So if I download
Uncle Frank, is the voice Uncle Michael, the voice keeps freezing.
Yeah. Okay, so now the instruction is downloaded and it's running. So if I press, you can see. Are you following? So I have this sensor. As I said, the limit is your creativity. I have this sensor, and if I press it, what happens? The fan turns. If I leave it, the fan does what? It stops. So the 2 states of this machine is turning on the fan or turning off the fan. And it is triggered by what? By this sensor. Are you following? So, or it is either on or what? Or off. Are you following? That is a 2-state machine. You have a sensor that feeds into the intelligent brick or the system and decides on one of 2 possible actions that the robot can perform. In this case, turning it on or turning it what? Off. Are you following? Are you following? So this is an example of a finite state machine. A 2-state finite state machine. So it's a finite state machine, but here there are only 2 states. And that is how we program a 2-state machine. In our next session, we'll be looking at how to program a 5-state machine. So we are going to be using this same example, but this time it's either going to go at a speed of 30, a speed of 40, a speed of 50, a speed of 60, or a speed of 70. Are you following? Are we there? We'll look at how to do that. It means we will need a sensor that will be able to detect when we should drive the fan at a speed of 30, when we should drive the fan at a speed of 40, when we should drive at a speed of 50. So what we will do in our next session, Alan got disconnected. Sorry. So what we will do in our next session, or the next set of videos you receive, we'll talk about 2 principles. It will talk about a different type of robot. What we've looked at in this session are finite state robots. In the next videos you receive, we will talk about continuous state robots. Then we'll come back and talk about 5-state robots. Are you following? So we'll revisit finite state machine, but under finite state machine, we'll look at 5 states where we can control this same fan, but at different speeds. Are we there? Are we there? So when I send you the link, watch the video first. The next time we meet, we'll program what we have in the videos, or we'll go over the concept, explain it like we have done in today's session, and then we'll go on to program the 5 states. We'll look at how to use the 5 switches we discussed. So you saw how we had the switch and gave it state 0, state 1, state 2, state 3, state 4, state 5. And we could have put different speeds under each state. All we will need is how to control each of those states. Are we there? Are we there? Any question from today's lessons? Any question?
Uncle.
Yes.
Uncle Michael.
Yes, sure.
Let's say you put together the code and
come again.
And then like the EV.
Come again.
What if you put together the code and you put on the EV ring? Is it possible that if, let's say, you do the code, you run the code, and but you have a lot of codes on the EV3, is it possible that so like let's say you put in the code, but like there's not enough storage on the EV3 and the switches and things, will it cut out?
No, it won't. It won't.
Okay.
It won't. So, what I'll need you to do is, if you have a robot at home, design a simple robot. Create your own fan, better than mine. Better than mine. Mine is not nice. Create your own ceiling fan. Connect your wire to your intelligent brick and program it to be controlled. When you are done with your control, have a short video and then submit it as your assignment for today. If you receive the videos for next week, watch it and try to see if you can create a 5-state for the fan. Use any sensor of your choice. You can use the ultrasonic sensor and say, if you bring your hand close to the fan, the speed should be increasing. If you bring your hand close to the sensor, the speed should be increasing. If you take your hand far away, the speed should be what? Decreasing. You can use that to trigger 5 different states. So try your hands on anything. But I'll send you videos for multi-state machines. So you can do 3 states, 4 states, 5 states, 6 states, even 10 states. You can do that. But for today's assignment, design a simple fan for 2 states. And mind you, WRO, there is RoboFest, there is an exhibition category where you are free to design something of your own and exhibit. You may be interested in taking part in the online exhibition if you are creative enough. I think Kofiwari's team is preparing for the exhibition. So they should open up their imaginations and create any fun and nice or creative solution they can come up with. So ask your questions. We have just about 8 minutes to our time. Ask any question you have. I'll be sharing the link for last week's video with those who don't have, and I'll also share the coming week's videos. By Monday close of business, you have the next set of videos, 3 videos. Watch them, and let's meet next week. When you go to the YouTube channel, subscribe, like the page, share it with others so that they can also learn alone.
I like
which YouTube?
Subscribe.
So the videos I send, they are on YouTube. I send YouTube links of what we have done today. I have a session explaining all of those concepts. So I usually send them a week ahead before we meet. So before you come, I expect that you have watched the videos and you have some basic understanding of what we are coming to discuss. The class is more in-depth, but the videos will give you an overview of what we are going to do. And it is also explanatory enough for you to be able to do things on your own. So I will share the link with all of you. I'll share the link with all of you. And then so I'll share the links with you for last week's videos. And last week's videos are what we have discussed today. I'll be sharing next week's videos on Monday. So when I share it, you can go there, and then if you finish your assignment, you can put that comment to the videos. Does YouTube allow video comments? So you can share your solutions. Or Sean, you can also have your own channel and be sharing your solutions. Sean is always creating. I say also. So if you have questions, let me have them. If you remember any question along the week, you can send it as comments under any of the videos. I will check and then respond to you. Okay? Is that fine? Okay. So if there are no questions, then
wait, I had one.
Okay.
Please, last time when I watched the videos, I downloaded it.
Sure.
So like, if we go over the things that we learned last time.
Come again.
Like the things that I know we go over, and I know the things we learned in the video to come into play next time. But like, I'm saying I downloaded the video, but like, will it like come into play like we go over like certain parts next week? I know to come into play into the actual code, but like we go over it next week, like certain parts for the code.
I seem not to understand you very well. But next week's videos will talk about a different concept. They'll talk about the different concepts. They'll talk about continuous time machines, and they will talk about how to implement a 5-state machine. But now you understand what we mean by states. States are the possible actions a robot can perform. 2-state means the robot is limited to only 2 sets of actions, like what we have. It is either turning on a fan or turning off a fan. Are you following? These 2 states. But in the next set of videos, you look at how to do 5 states or 10 states or 20 states. Are you following? Then we'll also look at something called continuous time machines, where the robot is not limited to any number of actions. So continuous, or let me say infinite state machines, they are not limited. They can do so many things. Like human beings, we have so many states. So we'll look at how to implement continuous time machines as well, which are not limited to a finite set of actions. Are we there? So in the next week videos, you receive videos on machines that are not limited to a fixed number of states, and how to implement a multiple state machine, like 3 states, 4 states, 5 states. I'll talk about calibration as well. So we'll look at about 3 concepts in the coming week. Okay, so you can download the videos and keep them so that anytime you want to revise, you don't have to go online again. Okay. Any other question? Joel. Joel, everything understood?
Sir Michael,
Good. Isaac.
What is that stake that is connecting the wood to the actuator?
Okay. So it is one of the EV3 pieces. Let me show you that. So look at the piece I just used. Can you see this piece?
Yes, yeah.
Usually we need to connect the wheel. So that piece,
Yeah, I've seen it.
and then because I did not want this to come out, you see, if I connect this way and I leave it, it will fall. It will fall. So I use this small piece to so that this is locked. Now it doesn't drop.
I thought it was bigger.
So it doesn't drop. And then I connect that to this. So assuming this was connected to the top of a helicopter, then depending on the speed, you may be able to build a machine that can lift itself, but that is not as simple as that. So I just want you to be creative. So that is what we have here. Okay. So submit your assignments to. If you finish it up, you can send that to me. You have my email. I used to send the links. So you can send that to me if you finish. I'll run it and see. Or I'll go through the code and see. But this one is a simple one.
Uncle, my please. My Gmail. I not get it. Please, should I link my Gmail?
You can when you program and it works. If you have a robot, you can record and send me on WhatsApp. I'll look at it. You can send snapshot of your code. You can just take a picture of your code and send that to me. That's fine.
Okay.
Alan. Alan, everything understood?
Yes.
Okay. Esther. Okay. Ernesto.
Uncle.
Are we good?
Uncle.
Yes.
Okay, good.
Uncle Michael.
I've heard from Isaac. Someone is speaking. Isaac.
No, it's not me.
So, Uncle Michael.
Yes. I'm listening. Okay, who are his team? Speak. I'm listening.
My motors are with Daniel.
Your motors are with Daniel. Ah.
Yes.
Okay. You don't have any motor with you. So next week.
No.
Don't worry. I'll come around. I'll be coming around. So I'll bring you some motors because next week we'll be meeting to prepare for the online RoboFest virtual competition.
Okay.
Next Saturday. So I'll be calling. We will have to make arrangement and start preparing for the competition. So we will work on that. Alan, I'll get you motors.
Okay.
Okay. Okay, so if there are no questions, then enjoy the weekend, have fun, and be creative. We'll meet next week. And I'll be sending next week's videos by Monday, close of business. Thank you all for joining. Bye-bye.
Bye.
Bye. Please, thank you.
Welcome, Sean.
Yes, sir. Okay. Bye.
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 Bye.